So again, about medical physics, lectures in general physics for medical science student by Dr. Hassan Moridi, assistant professor for theoretical nuclear physics at Taiz University, Yemen. Fluid mechanics. States of a matter: solid has a definite volume and shape. Liquid has a definite volume but not a definite shape. Has gas unconfined, has neither a definite volume or nor shape. Fluids. A fluid is a collection of molecules that are randomly arranged and held together by weak cohesive forces and by forces exerted by walls of a container. Both liquids and gases are fluids. Fluids do not sustain shearing stresses or tensile stresses. The only stress that can be exerted in the object submerged in a static fluid is one that tends to compress the object from all sides. So the forces exerted by a static fluid on an object is always perpendicular to the surfaces of the object. Density nodes. Density nodes is defined as the mass per unit volume of the substance, where R is the density, m is the mass of the substance, and V is the volume. The unit of density in C unit system is kilogram meters per meters cubed. The values of density for a substance vary slightly with temperature, since volume is temperature dependent. The various densities indicate the average molecular spacing in a gas is much greater than that in a solid or liquid. So such as substances like ice, we have rule 0917. For water, we have something like 8 alone. It's 1 on the 10 in the power of 3 kilogram per meters cube. Viscosity. Real fluids, especially liquids, exhibit a kind of internal friction called viscosity. Fluids that flow easily, like water and gasoline, have a fairly low viscosity. Liquids like molasses that are thick and flow with difficulty have a high viscosity. There are two different types of viscosity defined. The more common is dynamic viscosity. The other is kinematic viscosity. Dynamic viscosity: when a body is placed under transverse shear stress, sigma. Greek letter is your forces doing transverse forces acting on area. The resulting strain, epsilon, also Greek letter, is the tangential displacement x divided by the transverse distance L. Yes, sigma is equals to E epsilon, and F transverse divided on area equals to S multiplying on displacement x divided by transverse distance, whereas in the shear modulus, fluid flow undergoes a similar kind of shear stress. However, with fluids, we find that the stress is not proportional to the strain, but to the rate of change of strain. Ft transverse divided on area is equal to mu divided on dt. Yes, some are our derivatives on the dx divided on L. It's equals to mu multiplying on v divided on L. Yes, So dynamic viscosity, V is the fluid viscosity, the proportionally constant which take the place of the shear modulus is the dynamic viscosity. The C units of dynamic viscosity are Pascal second, Pascal multiplying on second. Other common units are the pores. 1p is 1/10 of Pascal's second, and the centipoise. So it's a 1/100th of Pascal second. Viscosity, especially liquid viscosity, is temperature dependent. You have probably noticed the form for everyday experience. Refrigerator map syrup is fairly thick, high viscosity, but if you warm it in the stove, it becomes much thinner, low viscosity. So, kinematic viscosity. Kinematic viscosity is defined as the dynamic viscosity divided by the density. Nu is equal to again mu divided on rho. So dynamic viscosity divided on density. C units for kinematic viscosity are meters squared per second. Other common units are Stokes. 1 Stokes and 10 in the power minus 3 meters squared per second, and centistokes is the 10th in the power of minus 6. So the viscosity of common liquids with on the temperature, you can see it at the table of different dynamic viscosities of the liquids, something like honey and peanut butter. Surface tension. Fluid is matter that has no definite shape and adjusts to the container that it is placed in. Gases and liquids are both fluids. All fluids are made of molecules. Every molecule attracts other molecules around it. Liquids exhibit surface tension. A liquid has the property that its free surface tends to contrast to minimum possible area and is therefore in a state of tension. The surface tension of the water allows the insect to walk on the water without thinking. The molecules of the liquid exerts attractive forces on each other, which is called cohesive forces. Deep inside a liquid, molecule surrounded by other molecules in all directions. Therefore, there is no net force on it. At the surface, a molecule is surrounded by only half as many molecules on the liquid because there are no molecules above the surface. Molecules inside the liquid with the surrounded by other molecules in all directions, and the molecule is on surface with half of this force because it's no molecules about the surface. Surface tension definition. The force of contraction is all right angles to an imaginary life of unit length tangential to the surface of a liquid. It's called its surface tension T or Y, or gamma. Gamma is the Greek letter. It's also the difference between F and L, whereas F is the force exerted by the skin of the liquid, and C unit of the surface tension is Newton per meter. Yes, surface tension. So some surface L, it's meters, your meters. Why the soap bubbles are spherical. Generally, a system under the influence of forces moving towards an equilibrium configuration that corresponds to minimum potential energy. The sphere contains the most volume for the at least area, minimum surface potential energy. There are no cubic raindrops. Capillary action. The molecules of the liquid exert attractive forces on each other, which is called cohesive forces. When liquids come to contact with the solid surface, the liquid's molecules are attracted by the solid's molecules, called adhesive forces. If the adhesive forces are stronger than the cohesive forces, the liquid's molecules are pulled towards the solid surface and the liquid surface becomes curved inward. In other words, water in a narrow tube. Incohesive forces are stronger, the surface becomes curved outwards. In other words, with mercury instead. This also explains why certain liquids spread when placed on the solid surface and wetted. In other words, water on glass, while others do not spread but form globules. In other words, the example is mercury on glass. The behavior of the liquids in both figures is called capillary action. And here is the formula about this capillary action. It's a height which you have to up or down this column of the liquid inside, and it strongly depends about the cosine theta. Here it's your angle, and highly depends on the radius of the this tube, the density of the your liquid, and pressure. At any point on the surface of the object, the force exerted by the fluid is perpendicular to the surface of the object. The pressure P of the fluid at the level to which the device has been submerged is the ratio of the forces to the area. So P is equal force divided on area. A pressure is a scalar quantity. It's no direction, it's not a vector, because it is proportional to the magnitude of the force. If the pressure varies over an area, evaluate dF, differential the force, on the surface of the area, differential the area dA, as dF equals to P multiplying dA. Unit of pressure is Pascal. Pascal is 1 newtons per meter squared. Variation of the pressure with depth. The here is on the picture, the parcel of fluid is in equilibrium, so the net force on it is 0. So, you could also say the resulting force, because the force is an additive, has an additive value, so you could actually plus them. If the fluid is at rest in a container, all portions of the fluid must be in static equilibrium. All points at the same depth must be at the same pressure. Examining the darker region, a sample of liquid within a cylinder. It has a cross-sectional area A. The liquid has a density of a rho. Yes. The three forces are downward force on the top, P0A, upward on the bottom, PA, and gravity action downward mg. The mass can be found from the density m is equals to rho multiplying on the of the body, volume of the body, the density on volume, and it will be the area multiplying on h. Since the net force must be zero, it's the our condition of equilibrium this body inside this volume. So solving for the pressure gives us the P equals to P0 plus rho gh. If the liquid is open to the atmosphere and the P0 is the pressure at the surface of the liquid, then P0 is atmospheric pressure. P0 is equals 1 atmosphere. 1 is multiplying on 10 in the power of 5 Pascal, atmospheric pressure. Pressure measurements, barometer inverted by Torricelli. A long closed tube is filled with mercury and inverted in a dish of mercury. The closed end is nearly a vacuum. Yes, measures atmospheric pressure as P0 rho argentum gh. Yes, 1 atmosphere is nearly 0.760 meters of a gigaton. So the this length of the column for the mercury inside the long closed tube give us the atmospheric pressure. Yes, manometer is another way to find the for measuring the pressure, because to work with the mercury it's very dangerous, so because it's poisoned. Device for measuring the pressure of a gas contained in a vessel. One end of the U-shaped tube is open to an atmosphere. The other end is connected to the pressure to be measured. Pressure at B is P equals P0 rho gh. The height can be calibrated to measure the pressure. The difference in height h, which is the sum of the readings above and below zero, indicates the gauge pressure. P is equal rho gh. The difference in height h, which is the sum of the readings above and below zero, indicates the amount of vacuum. Sphygma manometer. The manometer is a part of a medical device that measuring the blood pressure, which is called a sphygma manometer. There are many types of blood pressure measuring instruments. There is some manometer with the something what's standing in a tube like the mercury manometer, but it seems to me that we have another type of the liquid inside. It's something like the ancient manometer, antiquarius, and different type of the new manometers here, and some of them are very modern, and you have semi, some of them are semi the automatic, some of them are already automatic, absolutely, so you don't need to measuring and hearing by yourself. And some of them you need to, they have to phonendoscope they need the doctor to hear this sound of blood pressure, and the this glucometer inside is not in that range of the manometers, just a medical photo of them. So the blood pressure. Blood pressure is the pressure of the walls of the blood vessels. It usually refers to the pressure in large arteries of the systemic circulation. Blood pressure is expressed in terms of the systolic pressure, maximum during the heartbeat, over diastolic pressure, minimum in between two heartbeats, and it's measured in millimeters of mercury. Millimeters Gedragium, from Latin. Millimeters of meter is the real millimeters of this column of the Gedragium of mercury, like it was in ancient times, but now we didn't work in it that way, but we still have this explanation and these values. So about the surrounding atmospheric pressure, always it measuring in millimeters of mercury, considered to be zero, like atmospheric pressure is considered to be zero for convenience. Measuring blood pressure, normal resting blood pressure is in an adult is approximately 120 millimeters of systolic and 80 millimeters of diastolic, abbreviated, and 120 on 80 millimeters of mercury. Here is on the picture our mechanism of checking the blood pressure, to hear the sound when you're closing the artery by this this manjet, by this contaminant. We just use the special type of the manjet of this cabinet to close the arteria, and when you start to pushing down the pump, looking like PR pump, rubber PR, and starting to push a little bit the pressure of the air inside this manjet into the convert, and you are starting to open the arteria, and you're starting to hear the sound of the Korotkov, the noises of Korotkov. And when it starts, it will be your systolic pressure. And because we have the starting of the turbulence flow of the blood inside this vessel, inside the arteria, and when you start to hear the sound, it's your systolic pressure. When you stop to hear the sound, it's your diastolic pressure. It's actually starting to blood flow become the laminar. Laminar. So hypertension flow. Hypertension, it's a high blood pressure. Blood pressure increases when the heart pumps when the heart pumps blood more vigorously, or when arteries narrow, causing increased resistance to blood. In order to understand how narrowness of arteria can affect blood pressure, we need to imagine pressing a tube or a tube vest. If the tube is normal, you will see the result of this different type of the blood flow inside this vessel. Turbulence, yes, and laminar. Я занята, господи, ну. Absolute versus gauge pressure. P is equal P0.